Welcome to this session. In the previous session, we saw how to solve a recurrence relation with the help of iterative method. If you remember, we mentioned three methods of solving a recurrence relation. The first one was the iterative method. The second one was the method of characteristic roots. So in this session, we are going to discuss the method of characteristic roots. In the method of characteristic roots, the solution of a recurrence relation, it's called now the general solution. It is made up of two parts. The first part is called the homogeneous solution and the second part is called the particular solution. In this session, we'll be focusing on homogeneous solution. We'll talk about the particular solution in the next session. So the complete solution or the general solution of a recurrence relation is made up of two parts. The first part is called the homogeneous solution and the second part is called the particular solution. So let us say this is the recurrence relation that has been given to us: an plus c1 an minus 1 plus c2 an minus 2 up to ck an minus k is equal to fn. If you remember, c1, c2, c3 up to ck, these were the coefficients, and we are usually dealing only with the constant coefficients. So these are constants, and fn is a function which represents the entire, which is equating the entire recurrence relation. If fn is set to 0, this was also discussed in the previous session. If fn is equal to 0, then the recurrence relation is called a homogeneous recurrence relation. And if fn is not equal to 0, it is called a non-homogeneous recurrence relation. Now let us assume that we have been given a recurrence relation which is non-homogeneous in nature. So we'll find the general solution as being sum of two parts, the homogeneous solution and the particular solution. Now for finding the homogeneous solution, we start by equating fn to 0. If fn is equal to 0, this recurrence relation now reduces to a homogeneous recurrence relation. Remember, if fn is equal to 0, then the recurrence relation is called the homogeneous recurrence relation, and the solution to this homogeneous recurrence relation, RR stands for recurrence relation, is called the homogeneous solution. Now how do we perform that? We start by substituting an by r to the power n. So an will be substituted by r to the power n. An minus 1 will become r to the power n minus 1. An minus 2 will become r to the power n minus 2. A to the power an minus k will become r to the power n minus k. So this now becomes r to the power n plus c1 r n minus 1 plus c2 r to the power n minus 2 up to ck r to the power n minus k. Now we divide this entire expression by r to the power n minus k. So this now reduces to, if I have r to the power n over here and if I divide it by r to the power n minus k, so I get r to the power k plus c1 r to the power k minus 1 plus c2 r to the power k minus 2 up to ck is equal to 0. Now this equation is called the characteristic equation of the recurrence relation. This is called the characteristic equation of the recurrence relation. It might seem a little cryptic, but just wait for the examples. It will become more clearer. And the roots of this characteristic equation are called the characteristic roots. So what we have to do is we'll begin by first of all converting the recurrence relation to a homogeneous recurrence relation. Then we will convert this homogeneous recurrence relation to the characteristic equation, and then we will find the roots of the characteristic equation, right? Once we have identified the roots of the characteristic equation, now there can be multiple cases. See, these are characteristic equation. We find the roots. There is a possibility that the roots can be real and distinct, or they can be multiple roots, or they can be imaginary roots, or they can be multiple imaginary roots, and so on and so forth. So if we get real and distinct roots, let us say we are getting the roots as, let us say, r1, r2 up to rk. Remember, this characteristic equation is an equation of degree k. So obviously I'll be getting k roots over here. So if all the roots are real and distinct, that means I'm getting roots r1, r2, r3, r4 up to rk. These are all real numbers. None of them is imaginary, and they are all distinct. Then the homogeneous solution is b1 r1 to the power n plus b2 r2 to the power n and so on up to bk r2 to the power n, where b1, b2, b3 and so on are the constants to be determined by initial conditions. If the question has the initial conditions, you can use those initial conditions to find the values of b1, b2, b3, b4 and so on. And if the question does not have the initial conditions, then you can leave them as it is. You will express the solution in terms of b1, b2 and so on. Now the second possibility is that I have multiple roots. Now what is meant by multiple roots is that, let us say for example, the roots are R1, R2 and R3. The first three roots are coming same. The first three roots are coming same, and then I have R4, R5 and so on. What it means is R1 is a triple root. So the homogeneous solution will be given by B1 plus B2n plus B3n square multiplied by R1 to the power n. See, as R1 is a root of multiplicity 3, I've shown it over. I've taken an example that it is a triple root. So it will be B1 plus B2n plus B3n square. Say for example, if it would have been R1 is equal to R2 and then R3, R4 and so on, then if it was a double root, then it would have been An is equal to B1 plus B2n, simply R1 square, sorry, R1 to the power n. So as it is a triple root, so I'm having a polynomial of 3 terms. If it is a double root, it will be a polynomial of 2 terms and so. So b1, b2, bn, and then from this point onwards, as all the remaining roots are distinct, so I'll be following this convention. So I'll be having b1 r1 to the power n, sorry, b4 r4 to the power n plus b5 r5 to the power n and so on and so forth. Let's take another example. Say if I am having, let us say the roots are R1, 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 R2, R2, and then I have R3, R4, and so on. Now the equation will be something like AN is equal to B1 plus B2N plus B3N square R1 to the power N plus, as this is a triple root. Now R2 is a root of multiplicity 2. So I'll get B4 plus B5N R2 to the power N, and then from this point onwards I'll go with, say, let us say B6 R3 to the power N plus B7 R4 to the power N and so on and so forth. Now third case, if the roots are imaginary, if the roots are of the form R1 plus minus IR2, right? If the roots are R1 plus minus IR2, so the homogeneous solution will be given as AN is equal to B1 R1 plus IR2 to the power N and B2 R1 minus IR2 to the power N. If they are imaginary roots, we will get two roots plus one with the term addition term and one with subtraction term. Then if the imaginary roots are repeated twice, they may be repeated thrice or 4 or 5 times, but for simplicity I am taking just of multiplicity 2. So I'll have B1 plus B2n and R1 plus IR2n plus B3 plus B4n R1 minus IR2 to the power n. See, this is quite similar to what I'm doing over here. And if we get roots which are a mixture of these, I'll have a mixture of the above particular cases. Now let's see certain examples which will make it more clearer. Let's see the first example. It says the recurrence relation is given as AR minus 3AR minus 1 plus 2AR minus 2 is equal to 0. So we'll begin by, first of all, finding the characteristic equation of this recurrence relation. So what I'll do is substitute AR by, let us say, alpha to the power r. Let's use the term variable alpha. So I'll get alpha to the power r minus 3 alpha to the power r minus 1 plus 2 alpha to the power r minus 2 is equal to 0. Now divide this by alpha to the power r minus 2. So you get alpha square minus 3 alpha plus 2 is equal to 0. So once you have done a number of questions of this type, you'll be able to directly write the characteristic equation of the recurrence relation. See, I'll tell you how. See this recurrence relation, you can see this is the recurrence relation of order 2. R minus 2. This is the recurrence relation of order 2. So that means the variable will be have a degree 2. The characteristic equation will be in degree 2. So this will be R square, alpha square, alpha and without alpha. So this is the characteristic equation. This is the characteristic equation. Now if I solve this characteristic equation, this can be solved as alpha minus 1 and alpha minus is equal to 0. If I factorize it, it becomes alpha minus 1, alpha minus 2. That means this characteristic equation has now two roots, alpha is equal to 1 and alpha is equal to 2. So these are the two roots. Now see, these are real roots and distinct roots. See, in case of real and distinct roots, the homogeneous solution is given as, now I have only two roots, so I'll be having b1 r1 to the power n. See, this is the case over here, b1 r1 to the power n plus b2 r2 to the power n. Now r1 and r2 in this case are 1 and 2. So the homogeneous solution will be given as AR, once again I'll use this AR is given as b1 into 1 to the power r plus b2 into 2 to the power r. Now I know 1 to the power r is 1, so it will be b1 plus b2 2 to the power r, ar. So this is the required solution. As this recurrence relation was homogeneous to start with, it was not a non-homogeneous recurrence relation. From the very beginning, it was a homogeneous recurrence relation. So this solution is not only the homogeneous solution, but it is also the general solution. I don't have to find out the particular solution, as this recurrence relation was homogeneous in nature. Let's see another example. AR, this line I have drawn because the solution might be a little bit longer, so I have drawn a line in between. So AR minus 4AR minus 1 plus 4AR minus 2 is equal to 0. Now I have specified the initial conditions also. Remember, in the previous question, I did not specify the initial conditions. So the solution to the recurrence relation, So the solution to the recurrence relation was specified in terms of B1 and B2. But here, as I'm specifying the initial condition, so I will find the value of B1 and B2. Now, let's start. Let's first of all find the characteristic equation of this recurrence relation. So once again, substitute AR is equal to alpha to the power R. So I'll get alpha to the power R minus 4 alpha to the power R minus 1 plus 4 alpha to the power R minus 2 is equal to 0. Divide this by alpha to the power R minus 2. So you get alpha square minus 4 alpha plus 4 is equal to 0. So this is the characteristic equation of the recurrence relation. Now, solving this characteristic equation, I get alpha minus 2 whole square is equal to 0. So I have two roots, alpha is equal to 2 and 2. Now this is real and equal roots. The root 2 is of multiplicity 2. Now once again going back, if you see multiple roots, R1 and R2 suppose are same, so I'll have B1 plus B2 n R1 to the power n, right? So using it over here, so AR will be equal to B1 plus B2R, as the root is of multiplicity 2. Multiplicity 2. Multiplicity means how many times the root is getting repeated. So as the multiplicity is 2, so I'll have a polynomial with 2 terms. So B1 plus B2 are 2 to the power R. This is the solution of the recurrence relation. But the story is not finished to this point. Now I have the initial values over here. Now I'll use these initial conditions to solve for B1 and B2. Now I've been given, now I have A0 is equal to 5 by 2. Now let us put R is equal to 0. So I'll have B1 plus B2 into 0, 2 to the power 0. So I can write it as B1 is equal to 5 by. So I get B1 is equal to 5 by 2. Now A1 has been given as 8. Now putting R is equal to 1, I get A1 is equal to B1 plus B2 into 1, 2 to the power 1. So that means B1 plus B2, 8. Or I can write it as B1 plus B2 is equal to 4. Now B1 value I have already calculated as 5 by 2. So I can write 5 by 2 plus B2 is equal to 4. So B2 is equal to 4 minus 5 by 2. So I get it as 8 minus 3 by 2. So I now have B1 is equal to 5 by 2 and B2 as 3 by 2. So substituting these values in the solution, I get AR is equal to 5 by 2 plus 3 by 2 R, 2 to the power R. This is the solution of the recurrence relation. Let's see another example. AN plus AN minus 1 plus AN minus 2 is equal to 0. Once again, let's find the characteristic equation of the recurrence relation. This time what I'm doing is I'm writing it directly. So this now becomes, or rather, so let's put AN is equal to R to the power n. So it becomes R to the power n plus R to the power n minus 1 plus R to the power n minus 2 is equal to 0. Divide by R to the power n minus 2. You get R square plus R plus 1 is equal to 0. Now, when you try to solve this equation, you get the roots as R is equal to minus 1 plus minus root 3 I divided by. Solve it just like you solve any other quadratic equation. The roots are usually minus b plus minus b square minus 4ac divided by 2a. So this is minus b, a is the coefficient of r square, b is the coefficient of r, and c is the coefficient, the constant. So you get minus b plus minus b square minus 4ac divided by 2a. So you get r is equal to minus 1 plus minus root 3i. So sorry, these are imaginary roots. See, if there are imaginary roots, we get b1 r1 plus ir2 to the power n plus b2 r1 minus ir2 to the power n. So the homogeneous solution will be given by an is equal to b1 minus 1 plus root 3i divided by 2 to the power n plus b2 minus 1 minus root 3i divided by 2 to the power n. As the initial conditions are not given, so we'll write the solution in terms of b1 and b2. Let's have one final example. AR plus 4 plus 8AR plus 2 plus 16AR is equal to 0. Now this question is slightly different in the sense that in the earlier questions I was using AN minus 1, AN minus 2, but here I'm using r plus 4, r plus 2 and r. But once again, does not make any difference. So let's find out the characteristic equation of the thing. So substitute AR is equal to alpha to the power r. So I get alpha to the power r plus 4 plus 8 alpha to the power r plus 2 plus 16 alpha to the power r is equal to 0. Now once again divide by alpha to the power r, always divided by the expression having the lowest power. Always divide by expression having the lowest power. The lowest power in this case is alpha to the power r. So you get, dividing it over here, you get alpha to the power 4 plus 8 alpha square plus 16 is equal to 0. Solving this expression, it gives me alpha square plus 4 whole square, right, is equal to 0. That means it is alpha square plus 4, alpha square plus 4 is equal to 0. So the roots are alpha square is equal to minus 4 and alpha square is equal to minus 4. In other words, the roots are alpha is equal to plus minus 2i and plus minus 2i. So see over here, not only are the roots imaginary, but they are also repeated twice. So I'll have to use, once again, let's go back. If the imaginary roots are repeated twice, so I'll have b1 plus, I'll have b1 plus b2 and first root, b3 plus b4 and second root. So using this method over here, so I'll get the expression as AR is equal to b1 plus b2r. As the multiplicity of the roots is 2, they are repeated twice, so it will be a polynomial of 2 terms. So I'll get b1 plus b2r 2i to the power r plus b3 plus b4r minus 2i to the power r. This is the required solution of the recurrence relation. So this was how you will find the solution to a homogeneous recurrence relation. All the examples that I have taken today were homogeneous recurrence relations. In the next session, we'll see what happens when you get a non-homogeneous recurrence relation and you have to find out the solution, not just the homogeneous solution, but also the particular solution. Till then, thank you.